Class. It's been a long weekend, even though it wasn't a long weekend. So, not exactly sure what the game plan is with this class. Part of the reason why is I want to make sure that people take the exams on Monday. So, the exam is posted. It's on Monday. I just saw the look of shock and awe. We haven't gone over the last exam because there are still people who haven't taken it. So that's something that has to happen at some point. You may not be able to go over it before the next exam. And so that's about it. So now, how many people did the reading? All right, smart. So you guys did the reading. And notice, what did you read? You reread basically the section that you read before. But now you have the full-blown treatment of vectors. And does really anything change? No, not really. So there's only basically a few force problems that we can do now that we couldn't do before. But they are important. So let's actually start that. So the first one is what happens when you have, let's say, tension. You have an object that's supported by more than one wire, and not necessarily in an equidistant fashion. Like, for instance, if you look at that setup over there, I know it's a little bit difficult to see the string, but what you have is you have this mass being supported by the tension in this rope and the tension in this rope. And so now the question is like, well, what happens there? Physically, what is that arrangement? So let's actually go and do this. So you have some vertical support. Here's some vertical support. And then you have one. And then you have, I don't know, another. All right. Maybe something like this. Unfortunately, for some odd reason, there we go. How about that? So now it's definitely, are they going to be the same tension if they're supporting some mass? Yes or no? So, same tension? Yes, no, maybe so. And the answer is, we will see. Don't suppose anything. So what do you do, guys? On what? On the mass. That's right. So you do a free body diagram on the mass. Maybe before we do that, we should actually kind of show the coordinate system that we're going to use. So what coordinate system do you want to use? All right. So something like this. Plus x plus y. Okay? So, generally speaking, something I didn't say to the previous class, but I will today. Free body diagrams are on the AP exam. You cannot include the components. Write that down in your notes. On the AP exam, you are not allowed to include the components of a vector, of a force vector, in a free body diagram. Personally, I think it's idiotic, because really, why? I mean, to me, it doesn't make any sense. But when you get in the AP exam, just remember to not do what I'm about to do right now. All right? And you might want to put an asterisk on this. So, FT, I'm going to draw the free body diagram on the diagram. Or in other words, I'm not going to isolate the body and show the body separate. It just makes sense to just do it straight on here. So what are the forces on here? So which tension? Which one? What do you want to call this? Call this FT1. Call this. And where's FT2 directed? Whoa, be careful. Can we even talk about negative directions? Not really. Because it's in the positive y direction, but the negative x, right? So, but I understand what you're saying. Where is it going to be directed? That way. FT2. And last but not least, FG, right? And so now what are we missing here? Victoria, what do you think we're missing? These vectors are on. They're on angles. Each one of them is on an angle, so we're missing the angles. So let's actually construct some angles. Now we have a decision. How do you want to construct angles, guys? Do you want it with respect to one direction? Or do you want to be flexible? No flexibility? No way. No flexibility, Khalil. Well, what you'll see is I'm going to be inflexible at first and flexible later. Yes?
So whether or not you make the angle flexible is this dimensional of the problem?
Yes and no. I mean, the whole point is that you have to understand trigonometry. You can't just be a drone, right? You need to understand that, for instance, if I call this a positive angle, then the x component of my vector is negative, right? So when I go and write Newton's second law, I got to make sure that I account for that properly. You'll see that it's not so obvious when you actually do it the formal way. It's not so obvious. So let's actually take everything with respect to the positive x-axis. So then what's this angle going to be? What do you want to call that angle? Let's call it theta 1. And then what do you think this angle is going to be? Theta 2. So realize theta 1 goes from here to here. Theta 2 goes from here to here. I know you're having a difficult time seeing this, right? Because it looks terrible. I mean, even if I zoomed in, you couldn't make sense of it. So now, what do? We write down Newton's second law in each direction. But maybe we should write down each of these forces. And by the way, there is a theta 3. What's theta 3? 180? It's 270. Do you want to include that too? Or can we use our brains? See, this is what I mean by being flexible versus inflexible. Flexible means you recognize that this is a 270-degree angle, and then the force is going to be what? That force of gravity is going to be positive or negative? Negative, right? Because in our coordinate system, that's down. But whatever, let's be inflexible. All right? Call that theta 3. So now, in our own inflexibility, we go and we write things down. So we have, in the x direction, sum of the forces in the x direction equals the mass times the acceleration in the x direction. Right? The sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. But of course, this simplifies. Why does it simplify? So what's the acceleration in the x direction? 0. What's the acceleration in the y direction? Really? It's 0. Why is it 0? That's right. There's no accelerated motion. It's 0. This is called translational equilibrium. Translational equilibrium. And in fact, that's in something called static equilibrium. Static equilibrium is a little bit more restrictive. It means the body is neither moving, translating, or rotating. But we haven't gotten to rotation, so it's not even worth talking about. So now we need to sum up all the forces in the x direction. So what do we have? Ft1x plus ft2x plus fgx, all right, equals 0. What's ft1x? ft1 times the 1, correct. This is ft1 cosine of theta 1. What's ft2x? Yes.
I have a question.
Shoot.
For like the FT2 one, like, why is it negative?
Ah, you'll see. You want to explain it?
Because the way we define that coordinate system, if we figure out the components of it, the x component will be better than the component of x.
No, but she's asking, why don't we subtract it?
Oh, because when you find anything that, to subtract the two.
That's right. And this is what I mean. Sometimes the programmatic approach gets you in trouble because you were thinking, you know what? Let me subtract ft2x, correct? And then you would subtract ft2 cosine of theta 2, and what would happen? It would become positive. This is the danger of being formulaic. Does everybody understand what just happened? Who doesn't understand? Please raise your hand because this is very important. Okay. What now he's asking is, why didn't I subtract this? Because clearly ft2x is in what direction? Negative x direction. The reason is because when we defined our angles, we're defining all of them with respect to the positive x-axis. So when I take the cosine of theta 2, what do I get? I get a negative number, so if I subtracted it, it would become positive. And this is why I strongly urge you guys to use your brains. Do not do a formulaic approach. I'm going to do the formulaic approach, and I have to use my brains. So now, what's fgx? Cosine of theta 3. But what's the cosine of theta 3? 0. Why? Because the cosine of 270 is 0. But we can write it down. Right? Why not? We got nothing better to do. We're here. Okay? And so we get the following relationship. This is 0. So, because theta 3 is definitely defined. Okay? Now let's go in the y direction. By the way, does anybody have any questions about how I got ft1x is ft1 cosine theta 1? Anyone? All right, so you want to know, let me do this on the side. So let's draw the triangle. Here's ft1. Here's theta 1. Notice I can break up ft1 into two vectors, ft1x and ft1y. The cosine of theta 1 equals what? What's cosine? No, what is it defined as? Adjacent over hypotenuse. Remember this, because it changes depending on the triangle. So you have to always look at the definition of cosine sine. So definition of cosine is adjacent side, which is ft1x, over the hypotenuse, which is ft1. So therefore, ft1x equals ft1 cosine theta 1. And likewise, ft1y is going to be, that's right, by the same exact logic. So here, what do we have? This is where things get annoying, because, no, other way. In the net force in the y direction, we have what? We got ft1 sine theta 1 plus ft2 sine theta 2, right, plus fg sine theta 3. I'll even write sine 270 degrees. And that net force equals 0. And so therefore we have ft1 sine of theta 1 plus ft2 sine of theta 2, right, minus mg equals 0. Notice what I get minus mg? Sine 270 is negative 1. Be careful, it's a negative 1. Huh? What is fg? Fg is mg. Don't forget that. I know we have no memory. I know this. I've accepted this, that we have no memory. But let's at least try. Despite its futility, let's at least try. The force of gravity on an object is its mass times the acceleration of gravity. So, here we have our equations. What do? We begin solving. Do we see what do we have now? Can we see everything? Yes, we can. All right, so I'm going to write down what we have, and I'm going to continue solving it. So, actually, you're going to tell me what we have on a new page. What are our two equations? Our two equations are ft1 cosine theta 1, right? Right, and how about that? Even better. Equals mg. Carried over the mg to the other side. So now, solve for ft2 in terms of ft1. What do you get? ft2 equals, come on, guys. Very good. So you guys are getting quick. And then what do I do with ft2? Plug it in. So you get ft1 sine theta 1, right, minus ft1 cosine theta 1 over cosine theta 2 sine of theta 2 equals mg. Now what? Common denominator. Solve for ft. What do we get? We can factor out ft1, right? Then what? Multiply the first term by cosine of theta 2 divided by cosine theta 2. Meaning we're multiplying it by what? What? By 1. By a strategic 1. So that becomes sine of theta 1 cosine of theta 2 minus cosine of theta 1 sine of theta 2, all divided by, what was the common denominator? Cosine of theta 2 equals mg. I'm going to do something pretty clever. I'm going to factor out negative 1. When I factor out negative 1, what happens here? That becomes, what do? They flip. So you get negative ft1 over cosine theta 2 times what quantity? Sine of theta 2 cosine theta 1, right, minus sine theta 1 cosine theta 2. And you're probably wondering, Mr. Khalil, why are you doing that? It's not the sum, but the the difference, but of specific, both of them are the difference. In the first case, what is this thing here? What is this expression in the numerator? See if you guys can identify it. It's not double angle formula because theta 1 and theta 2 are not the same. It's what expression is it? You guys had to derive something along these lines, or I derived something along these lines. This is the sine of theta 1 minus, this right here is the sine of theta 1 minus theta 2. Now the question is, why didn't I want to use that? Why instead did I factor out negative and in fact got what? The sine of Why did I prefer this? The answer is, we will see. So, bear with me. So you have ft1 is equal to negative mg cosine of theta 2 over the sine of theta 2 minus theta 1. But I'm going to go way back, go into the way back machine. All right, so this is ft2 in terms of ft1. So ft2 is equal to negative ft1 cosine of theta 1 divided by the cosine of theta 2. So ft2 is equal to negative mg, which is positive mg cosine of theta 2 over the sine of theta 2 minus theta 1 times cosine of theta 1 over cosine of theta 2. Notice what happens to cosine of theta 2's? And you get all right, so now I got a question for you. What's the sine of ft1? Is it positive or is it negative? Why is it positive? No, tell me. Why is ft1 positive? First, can it be negative? Is it allowed to be negative? Why? No. Whenever you solve for forces, that quantity always is going to be positive. Why? Because that quantity represents magnitude. We assign direction in free body diagrams. But whenever you solve for an F, it's always a positive quantity. Now the question is, why is this positive? Can someone tell me? Look at it. What's the cosine of theta 2? A negative number. So that negative times that negative makes it positive. What about this guy, the sine of theta 2 minus theta 1? You sure? Why is it positive? To be careful, that's theta 2 minus theta 1. Let's go back to the drawing. Because now the question is, we're going to go back to, why exactly did Mr. Khalil change the sign? In other words, why did I want to find this versus this? Anyone? What does theta 2 minus theta 1 represent? That's right, it represents this angle. Let me show you on the physically. It's this angle. This is theta 2 minus theta 1. Notice, theta 1 minus theta 2 would have been, it would have been something crazier, like it's it'd been this. There you follow that? So it's just from the standpoint of drawing physical meaning from the expression, it's much easier to draw physical meaning from theta 2 minus theta 1 than it is from theta 1 minus theta 2. So let me go back. So now, and notice something else, guys. I'm using my trig identities. There is a reason why. There is a method to the madness of what I did earlier in the unit. Okay? Is FT2 positive? Yes or no? The answer is why? Because the cosine of theta 1 is a positive number. So FT1 is positive and FT2 is positive, and that's how it better be. Otherwise, you're making an error. So now, can someone tell me where the tension goes to infinity? Take a look at this. Here are our expressions. FT1 equals negative mg cosine of theta 2 over sine of theta 2 minus theta 1. When does this go to infinity? When does the force of tension diverge is the proper term? Anyone? Well, something goes to infinity when the denominator equals 0 or approaches 0. So what would make that denominator approach 0? Yes? That's when the sine is equal to 180 or 0. So what situation is that? When theta 2 equals theta 1. What does that physically look like? That looks like this. We move this thing over to here. Why would the tension go to infinity? Is it possible that if we move this to this spot, that this could even be at an angle? No, what would happen? It would swing over and then just point directly below. In other words, what this points at is that you need to have a separate angle for this thing to lie on any angle. That's why it diverges. That's why it goes to infinity. Questions on this? All right, great. Now you guys get to tell me what that mass is. What is the hidden mass? You're like, this is too early for this. All right? So you guys need to tell me then, what is that hidden mass? And you need to figure it out yourselves. Look at it. You need some information here. Do I have to get off, Khalil? My brain hasn't started yet. So we got some information. But don't be mindless. Don't be mindless. So, what is this dial on? What is that dial telling you? You guys are going to need to get up and see this. You're so reluctant to get up. You're going to be planting yourselves in those seats all day. So, that is the force of tension. That's right. So that's the force of tension. And then notice, what is that? That's angle. With respect to what? Yeah, but the question is, what angle is it? Is it this? Is it that? What is it? You sure? Wait, you sure? Why didn't anybody bring any paper over here? Bring your paper. You can draw on the desk if you want. All right, finally. So draw out the tensions here. You sure?
No.
So how do you want to do this? Do you want to do this with respect to the positive x-axis, or do you want to be flexible? Flexible helps here. Flexible helps. So be flexible. So now, this is where the tension goes, in the direction of the tip, right? So now if you look at this, with respect to the x-axis, that's going to be what? It's going to be this angle, which is 60 degrees. In other words, these are what, vertical angles or something? So FT1 is on a 60-degree angle. And what's the value of FT1? 1. Notice the value is always positive. Your forces must always generate positive values because those are magnitudes. So this is 1 at 60. What's this? What is this angle? So where is this vector pointing? This vector is pointing that way, right? At what angle? What is this?
So it's one. Either 125 or 135.
What? Look at this. That says 53 to me. So it's, you have to add to 60. Why do you have to add to 60?
Wasn't that what the other thing was?
Well, okay, but that's the other thing. But why do you care about that thing? Is that what you're measuring it with respect to? No, you're measuring it with respect to one of your coordinate axes. 133, you sure about that? Wait a second. So 53, well, how'd you do that? Plus 180? Was that? What? Are you sure it's 53 plus 90? Look at this. You need pencil. You can't figure this out looking at this. You need a pencil and paper. Come on, guys. This is... What you know is that this angle is 53 degrees.
Isn't it 133 plus 180?
I was thinking it's 180 minus.
Wait, so which angle are we trying to find?
So you think it's 180 minus 53. And how'd you get that?
Because if it's 53, well, yeah, actually, it depends on.
No, I think you're spot on. If you take a look, right? If you take a look, that angle equals that angle, right? And so that angle is 180, and you're subtracting 53. So what is that?
27.
It's 132.
Was it?
127.
127. You've got the big stuff here. I just can't add. It's okay. I can't either. All right, so now it's 0.8 or 4/5 at 127. And now what I challenge you to do is to not be mindless.
Wait, how do we get 1.3?
Because it's 180 minus 53. And you should draw it and really prove to yourself. Ah! Yes. Shoot. That's your sum for the mass. You could do that, or you could not be mindless. Let's try it. So to not be mindless means what? You write down these vectors, you break it up into its components, and you really kind of just bang it out. So this is 1. That's 60. That's 53. That's 4/5. This? 4/5. So what I'm trying to kind of draw you guys away from is just memorizing formulas. Give me another minute. Oh, I should probably take attendance. It's a great time. Chloe and shocked at how many people didn't go. Tarana, Allison, Sam, John, Ellie. To the music trip. Right? It's today, right? You're like, whatever. You didn't want to miss this class? Well, all the other classes you could have missed. Oh, okay. All right, so what you guys got? So let's actually do this. So, I'm doing in blue or whatever color this is. So notice, what type of triangle is this, guys? 30, 60, 90, right? So what's the proportions? So this is, so therefore, notice the hypotenuse is 1, right? So that's going to be double the shortest side. So that's going to be 1/2. And that's going to be √3/2. Right? And what is this? 53, 37, 90? That's a 3, 4, 5. So, if you take a look, opposite the 37 is going to be 3/5 the hypotenuse. So 3/5 of 4/5 is 12/25. 4/5 of 4/5 is 16/25. So looking at this, maybe we need to actually put this kind of on the same. What's √3/2 roughly? Anybody know? What's √3 approximately? Anyone have a way of estimating √3? As a fraction? Well, consider this. What does the square root of 3 mean, guys? That's right. If I say x equals √3, that implies that x squared equals 3. So let's see if we can actually approximate that with a fraction, like a perfect square. What perfect square fraction can you make that equals 3? And be careful. A perfect square fraction whose square equals 3. Whose square equals 3. How about 49, or it's close to 3. You can't have it equal 3. What about 49 over 16? Right? 49 over 16, is that approximately 3? It's pretty close, right? So if x squared equals 49 over 16, right, that's approximately 3, then x is equal to 7 over 4. So in other words, the square root of 3 is approximately 7 over 4. And you can do this with the square root of 2, too. Like, for instance, give me a fraction whose squared is close to 2. Come on, guys. Fraction whose squared is close to 2. Come on. Fraction whose squared is close to 2. You're like, this is too early. How about 100 divided by 49? Right? That's pretty close, right? And so now, is that greater than 2? That's not greater than 2? So that's greater than 2. Right? So in other words, a good approximation for the square root of 2 would be 10 over 7. Right? In fact, you'd say that's greater than the square root of 2. And if you want to even do better than that, watch this. I want a number whose square, I want a fraction whose square is slightly less than 2. Anybody know one? 49 over 25. 49 over 25 is less than 2, right? So the square root of 2 is what? Square root of 2 must be greater than 7/5. So you want to get a really, really good approximation of square root of 2. Guess what you'll do with these two? You'll average them. So let's average those. 10 over 7 plus 7 over 5, right? Divided by 2. What do you get? 50 plus 49, which is 99 over 70. And how is that? How good of an approximation is that? Yeah, right? So, so in other words, we have an approximation now for this. Root 3 over 2 is approximately 7/8. Right? So if you take a look at this, what are those? So you have 7/8. Woo! He's growing so fast. Plus 16 over 25 is root 3 over 2. Right? And what is that balancing? So minus, that's the vertical direction, right? Minus mg. And let's call g just 10. $10m. And that equals 0. Solve for m. So you have 7/18 plus 16 over 25 over 10 equals m. What do you got? What do you got? What's up?
No, why is it still 7/18?
Who knows? This is why I don't do I can approximate square roots in my head, but I can do crazy algebra, but I cannot actually just write down numbers. I just want to point out this is the danger of going too far in math. And this is widely understood in the mathematics community. People who go too far, forget it. It's over. They can't do any of the simple stuff anymore. So what do you got? 0.15. Guess what that mass is? 0.15. In other words, 150 grams. There you have it. 150 grams. Physics works. So, we turn our attention to this apparatus here. And what do you have? Come take a look at this. And what I want you to do is I want you to draw this, solve it for homework tonight. Tell me what the mass is. All right. All right. So you're looking at this. This took me 3 hours to set up. Huh? Tell me what this is. All right. So let's take a look. That is 1,200 grams. That is 900 grams. This is you should take a picture of this. This is a 90-degree angle.
The angle in the center.
That is a 90-degree angle. Yeah. That's a 90-degree angle. Okay? This is parallel to the plane. So these two are parallel. The length of this is 120 centimeters. The base is 96 centimeters. And the height is 72 centimeters. 96, 72, 120. The mass being supported by this pulley is 1,200 grams, 900 grams. What is the mystery mass? Make sure that you guys have the picture.
What were the stuff that was not parallel?
This
That's parallel to the.
is parallel to the track, and this is perpendicular to the track. What angles? I don't know.
That one's 90.
You want to know what angle this is? That's a 90-degree angle, Vicky.
That's about all we got.
Right, well, I gave you the sides. This side is 96. This is 72. This is 120. Yes, and you know this is a right angle. The track supports nothing. It's just there as a reference. So, enough of that. Let's go to the inclined plane. Here's a question. I have a question for the class. Do you find these useful, these types of setups useful? Really? Physically, yeah. So now let's take a look at the inclined plane. And the question is, the first question that should be going through your head is, if I take a block, and if there is or is not friction, what is the acceleration of this thing down the plane? So what is the acceleration of this object down the plane? Do you want with friction or without? Pick your poison. All right. Some people are like, cyanide. No, hemlock. No. All right. So let's pick hemlock. Huh? Hemlock? Hemlock, it's without, I think. Let's do with friction, because I think you guys are sophisticated enough to actually be able to do this problem with friction. So we draw it's totally pointless. So we draw an inclined plane. There we go. We have an angle, theta, that disappears. This is a right angle. And here is a block. What are the forces acting on the block? Let's do a free body diagram first. Gravity goes where? Straight down. So this is Fg. What's next? Normal force. Which way is normal force? You guys are good. You guys are real good. Here's Fn. What else? Friction goes potentially up or down the plane depending on what? The motion of this thing. That's right. But let's assume that we release it from rest. So friction is going to go up the plane. Now what? Now we need to pick our coordinate system. What coordinate system is the most convenient? I'm going to tell you something right off the bat. Before I even answer that question, what do we have to do? We have to nail this plane to the ground. So now that we got a good carpenter to nail this plane to the ground, right? Like, how'd you get the nail? How'd you get the top of that nail in there? So you would want to do your coordinate system like this. By the way, if we did not nail this plane into the ground, guess what? We could not use that coordinate system. Why? Huh? Because what? That's right. And so therefore it would not be what? In other words, what would happen to that coordinate system? It would no longer be a inertial reference frame. It would be a non-inertial reference frame. Newton's laws would not be valid. Why? Because the plane itself would accelerate, which means your coordinate system would be accelerating, which means Newton's laws cannot be applied. That's right. It would be accelerating, which is why the safest way, so like, you know, for really advanced students, if you're interested in seeing a proof of this, of seeing how things change with an accelerated reference frame, come see me. It's a great problem. you would need to set up coordinate axis outside the plane. But anyhow, now that we have our coordinate system, what do we need to do? We need to break down some vectors. Which vector do we need to break down? Y. Very good. It's not directed along the lines of our coordinate system. See you later!